All right, grade 6, our big idea for data continues to be collecting, displaying, and analyzing data helps us to solve problems and understand the real world. Our concept specifically for today is to demonstrate an understanding of analyzing graphs and drawing conclusions, and specifically knowing the difference between discrete data versus continuous data. This is Unit 7, Lesson 3, and again there are some other sources, so it won't all be found in your textbook. All right, let's take a look at an example of a graph. Here we have the Hard-Headed Helmet Company, who wanted to find out how many of its bicycle helmets had been sold in the last 6 months. The company surveyed 10 bike stores in Manitoba. And here we have the table of their data. Remember, a table is not a graph, it's just a chart. And it's a different way of collecting the data, not displaying the data. Okay, so in April they sold 12 months, May 21 helmets, June 56 helmets, July 63 helmets, August 37 helmets, and September 18 helmets. When we sell helmets, only whole numbers of helmets can be sold. For example, you can't sell half of a helmet, or a store cannot sell 12 3/8 helmets. So this graph has to be a series of points that are not joined, so they do not be joined, cannot be joined, excuse me. And this data is discrete. Okay, when it is in whole numbers, it can't be sold in halves, or it can't be shown in halves. It is considered discrete data, and you do not join the dots. Okay. There are actually gaps between these values. Okay, so when we jump from April at 12 to May at 21, it's not like that's continuously rising. That is a jump up to 21. A couple things to help you determine whether or not it's discrete data is that usually discrete data represents things that can be counted. So if something can be counted, it is usually discrete data. And you can see this is a series of plot points. It is not joined. It is discrete data. They've done a good job in graphing. They have a very specific title, number of bicycle helmets sold in the last 6 months. Here they have the month, and each of the months is a line. Remember, we want it to be a line, not a space. The number of helmets sold, we go up to 63 as our highest. So they've decided to count by 20s. I probably would have counted by 10s just to make it more specific, but 20s is fine. So they've counted by, well, actually they have counted by 10s because they've got a line in between each time actually. So 10, 20, 30, 40, 50, 60, 70, and 80. Remember, you have to count by intervals, so by 2s, by 5s, by 10s, by 20s, etc. And they have plotted their points appropriately. So April was 12 helmets. It's a little bit more than 10, so it gets put just a tiny bit above 10. May was 21, so it's just slightly above 20. June was 56, so it's about halfway between 50 and 60, a little bit more than halfway, and you can see that there. July was 63, a bit above 60, not just right above the line because it's a little bit more than just 61, for example. August at 37, very close to 40, and September at 18, very close to 20, just underneath that line. And from this table, we can make conclusions. So from the table, we can see that the greatest number of helmets was sold in July, okay, because that is the highest point on the graph. We could say that June and July had the most helmets sold with a difference of 7 to make that a very specific conclusion. We could also say that the least number of helmets were sold in April and September. And logically, we could say this makes sense because bike riding weather begins in April, so you might start looking for helmets then, and ends in September. So most people who want to have had a helmet, who want to do some bike riding, probably have already bought it. Those kinds of things can also be concluded from the, or inferred actually, from the information, not a conclusion from the graph. But remember, when you're doing conclusions, you can't just tell me about one point. So you couldn't just say, in May, there were 21 helmets sold. That's not a conclusion about the graph, that's reading one point on the graph. So just be careful about that. Here we have another graph. We have a table of information to graph first of all. So here's our table of information. We are looking at Leah's height and how it changes as she gets older. So we have here from 2 all the way up to 19 years of age, and she's at 83 centimeters up to 162 centimeters. All right, so continuous points on the graph are joined by line segments. These points on the line between the plotted points have meaning. So, for example, it's possible for Leah's height to have been 117.5 centimeters when she was 6 months and 3 years old. Let's take a look at this graph. I'll just enlarge it here so you can see. At 6 years and 3 months, well, it's a little bit after 6. So yeah, we can see on that line, it's still continuing to rise. And when we grow as people or plants or whatever, we don't jump from one height to the next. We are constantly growing. So we can have decimal points in there. So when we can have decimal points, when we can have half of something, then that data is continuous. It's continuing to grow. It's continuing to rise. It's continuing to drop. That equals continuous data. Oops. Okay, and then the lines do need to be joined. So let's continue to look here. From the graph, we see that from 2 to 16 years of age, the line segments go up to the right, so she's continuously growing. This shows that Leah's height is increasing. From 16 years on, the line segments are horizontal, side to side. And we can see that here. She has then, we can infer that she has stopped growing because her height is the same from age, well, almost really 15. But let's take a look at our table. Well, we can see it's actually 16. So from 16 to 19, there has been no increase. So we can infer that she's stopped growing. What other kind of inferences can we make from this graph? Well, let's enlarge it here so we can see it a bit better again. What could we infer? Well, an adequate conclusion would be that she was at her shortest at 2 and her tallest at 19. That doesn't tell us a whole lot. We could infer that she had grown her most by the looks of it. Let's just look carefully here. Yep, she's grown the most between the ages of 2 and 3 with a growth of approximately 10 centimeters approximately, a little bit less, maybe 9 centimeters from looking at those points. If we look carefully at the table, we can get a more specific answer, but that would be a good, excellent conclusion. We could say that she grew the least between 10 and 11 years of age with really probably looks like about 1 or 2 centimeters of growth. Those kinds of things would be things we can conclude from this graph. So this type of graph is called a line graph. When we join those points together to make a line, it's called a line graph. It shows continuous data, and remember, continuous data is something where we can have decimal points, and we can have a half of something. Then it is continuous data. It can include any value between the decimal points. It can include any value between decimal points. Often is things like time, money, temperature, measurements of some sort, such as length, mass. Those kinds of things are all continuous. They're continuously increasing. All right, let's do some practice now with your elbow partners. Reminder, continuous data is data such as any number, or that could be any number, such as the height of 2.58 meters. Discrete data, and I'll write it over here so you remember it, cannot be half of something. It has to be whole numbers. And it's often something that can be counted. So, knowing that with your elbow partners, try to identify whether or not the following examples are discrete data or continuous data. I'll read through them and then press pause and discuss with your elbow partner which one you think it is. Again, you do not need to have the same answer as your elbow partner, but use that conversation to assist you in determining your final answer. So, A, the number of questions on your weekly spelling tests over the course of a year, continuous or discrete data. Press pause and do that now. B, the height of a sunflower plant over the course of a summer. Press pause and do that now. C, the weight of a grizzly bear over the course of a winter, discrete data or continuous data. Press pause and do that now. D, the number of grizzly bears in one particular area over the course of the summer, discrete or continuous data. Press pause and do those now. Make sure to discuss carefully with your elbow partners. All right, so let's take a look. The number of questions on your weekly spelling test over the course of a year. Well, is that going to be something that can be counted? Is it in whole numbers, or can you have 0.5 of a number in between the weeks? Well, no, you only have one every single week, and that isn't growing or decreasing between the weeks. It's week 1, you have 12 out of 15, for example. It's not growing over week 2. Week 2, you have an actual amount of, say, 15 out of 15. But that can't change. So this would be considered discrete data. Let's take a look at the next one. The height of a sunflower plant over the course of a summer. Well, remember when things are growing in height, they're constantly growing. It doesn't just jump. So there's a constant growth from month to month. So that would be continuous data. The plant can be 6.54 centimeters tall, for example. The weight of a grizzly bear over the course of winter. Well, again, we know measurements are often continuous. Is it going to be able to have a decimal number? Well, yeah, in between they can be a decimal number. It could be 125.6 kilograms or whatever that might be. I'm not sure how much grizzly bears weigh. But that would be continuous data as well. And the last one, the number of grizzly bears in one particular area over the course of a summer. Well, definitely in whole numbers. Can you have half a grizzly bear? Not really. So that would make this discrete data. All right, one more thing I wanted to show you. Here we have Nathan's growth, in years from age 8 to 16, and it's displayed in height and in centimeters. But you'll see these odd little zigzags. I believe they're called breaks. I haven't been able to find any information about the specific name of this, but I have been told it's a break. So what this little thing helps you to do is it helps you to jump when you're numbering. So remember, we've talked over and over again about your numbering has to be in intervals. It has to be in ones, it has to be in tens, it has to be in fives, whatever. This little thing allows you to jump and not count by that particular number. So for example here, we've recorded the growth at age 8, which starts at about 125 centimeters. So that means we would have to be counting, and then after that it goes very small jumps. So like by tens is what we've got here. So if we were counting this, we would have to count all the way up to 120 by tens, and that's a lot of information here that's going to be empty in that graph. So this break allows you to skip that. Okay, so your break is drawn like that. It's a zigzag line within the numbering. So down here we've got the 0, and then here she's jumped to 100, or he, and then the next one is 110, and again they've numbered the lines and so on. You can only use a break once in an axis. Okay, so you can see they've also used it here. They didn't want to number from 0 to 8, so they've used the break there as well. It can only be used once on each side. So I cannot have it again in the middle here. Okay, that does not work. I cannot do that. The numbering, that should be numbering, forgot the G there in my typing, before and after must still be in the same interval. So if I happen to count below here, say I had something smaller that I was recording, and I counted below here in tens, oops, that would have to be 20, that would have to be 10. That's okay, but I can't down here be counting in fives and then up here count by tens. I have to use the same interval or the same scale. Okay, so there might be instances where you find the break or the jagged line helpful. You're welcome to use it, but again, you can only use it once for each side, and your numbering before and after must still be the same interval or the same scale, so by tens or 50s or 2s or whatever it might be. All right, and when you're working, just a reminder, we're looking for excellent conclusions that include specific info about, for example, the difference. We had the bike helmet graph. The highest jump in helmet sales was between May and June, with 35 more helmets sold. That specifically compares 2 dots on the graph. It also tells specifically the difference. That's what makes that an excellent conclusion. All right, you're on your own to be making graphs and then analyzing them. Page 261 and 262, numbers 1, 2, 4, and 5. Remember when graphing to use all of the points we've talked about, numbering the lines, remembering all of the titles, making sure it's on graph paper, and so on. And when you're drawing conclusions, work to make them excellent conclusions with specific information in them. Do not just tell me about one dot. That's not making a conclusion. That's reading a graph. And when possible, or when the question asks, determine if it's discrete data versus continuous data. Discrete data, remember, is one point, whereas continuous data can be in decimal numbers. It can be half of something, and so on. Remember, as you're working, if at any point you have questions, that you do ask.